operation of protection systems depends very much upon what is happening in the power system and our ability to measure these conditions. In this tape, we're going to look at ways to help us monitor and understand what's going on in the system. First, we'll look at features and limitations of the first link in the chain, that is, CTs and VTs. We already know from earlier tapes that sensing information is provided to the protection system by coupling the relay to the load circuit through instrument transformers. Current transformers, CTs, and voltage transformers, VTs, step down the power system current and voltage to safe working levels. This provides significant protection to the relay and also to personnel working on the protection equipment. Low voltage and current also permit the relay equipment to be made small and precise. Typically, the relay will work at, say, 5 amps and 120 volts. The instrument transformers are a critical component of the protection system, and consequently, they must be accurate. It's vital that the voltage and current provided to the relay from the transformers be a true representation of the current flowing or voltage level at a specific location. As we'll find out later, this may not always be the case. Instrument transformers conform to the normal relationships between primary and secondary windings. For example, let's say the turn ratio on this current transformer is 1 to 50. If the primary current is 250 amps, what is the value of secondary current? This is equal to the turn ratio, 1 over 50, times the primary current. That is, 250 divided by 50 equals 5 amps. Both the primary and secondary of a CT are built with relatively few turns of heavy wire, and this results in low impedance. This is desirable because if the impedance were high, it would create a high voltage drop in the load circuit. This CT is called the window type. It is also known as the straight-through or donut type CT. The primary winding is the power conductor that passes through the window. Since the conductor goes straight through, it is considered to have only one primary turn. The internal winding is permanently assembled on the core to form the secondary. A variation on this is the split core CT. It has a secondary winding permanently assembled on the core, much the same as the window type. The split core CT opens up, allowing a power conductor or bus to be placed through the middle of it. Another type of CT is this toroidal type, which is often used at lower voltages. The magnetic core is in the form of a ring. The 3 phase conductors pass through the ring, and any out of balance due to ground fault produces flux in the core. The secondary winding feeds current to a ground fault relay. And here is a bar type CT. This type is equipped with both primary and secondary windings, with the primary having again only one turn, while the secondary has many more. CTs are normally marked with their rating on the nameplate. For example, a 400 to 5 amp rating speaks for itself. 400 amps flowing through the primary will produce 5 amps in the secondary. This would be used where the anticipated maximum load current is just below 400 amps. But you will often see something like this, 600/300/5 rating. This rating indicates that the secondary of the CT has a center tap. The outer tap will provide twice as many turns, so the ratio will be twice as high, that is 600 amps to 5 amps. Often a large number of taps are provided so that the CT can be used for various applications.
Note that in all cases, the rating of the secondary is 5 amps.
For the relay, the most important aspect of the CT is its accuracy in reflecting the current at fault levels, which may be at least 10 times normal load current.
Now, CT performance. In an ideal CT, we just saw that the ratio of primary to secondary current is the inverse of the turns ratio. However, the core must be magnetized, and this is done by using a small amount of the current supplied to the primary. This additional primary current results in distortion of the current that is induced in the secondary. Because of this, 2 errors occur. 1, a ratio error, and 2, a phase angle error. To compensate, correction factors are calculated and provided by the manufacturer. This diagram shows a typical ratio correction factor curve for a current transformer. You can see that the correction factor is very small indeed for normal loads, about 0.3%, but the error increases significantly as primary current increases above rated value. And here is the correction factor for phase angle. The correction is shown in minutes of a degree. You can see that the error is very small, less than 1 degree.
The phase angle error is important in revenue metering, but it really has little effect on relay performance. In fact, for relay operation, we're really concerned that accuracy is good for much higher values of current, say 10 to 20 times normal full load current.
Standard classification of CTs is based on allowing 10% error for current flow up to 20 times rated value. The main characteristic affecting CT accuracy is that of magnetic saturation. What do we mean by this? Well, it's really a problem of overloading the core. The amount of magnetic flux circulating in the core of the transformer is, of course, proportional to the current passing in the primary. When primary load current increases, then magnetic flux in the CT also increases. But there is a limit to how much flux the core can hold, depending upon physical size. At a certain point, the core becomes saturated, and the flux will no longer increase in proportion to the primary current. Consequently, the secondary current will no longer follow its fixed relationship with the primary. Remember, it is the flux which creates the secondary current. This graph shows a typical saturation curve. Within its operating range, that is up to around 20 times rated current, the secondary current retains close correlation with the primary. But as the primary current increases beyond the knee of the curve, the secondary current is no longer accurate in representing the primary. In other words, the CT becomes non-linear. This particular curve is for a burden of 1 ohm. But look, as the burden is increased to 2 ohms, and here to 4 ohms, distortion starts earlier. At 4 ohms burden, the CT is accurate only to 10 times rated. The term burden is used to indicate load on the secondary of an instrument transformer. The accuracy of the CT at high current flow will be considerably reduced if we add too much burden to the CT secondary. This would occur if we added too many relays and other equipment to the secondary of the same CT. By adding more relays, more current coils are connected in series, so increasing the impedance. The transformer must now produce a larger output voltage so as to force the same current through the higher impedance. To achieve this, more flux is needed, and therefore more exciting current is required from the primary. As a result, distortion increases and accuracy of the transformer is reduced. In sum, then, as the burden increases, the overall accuracy of a CT decreases. Remember, rated current on the secondary is normally 5 amps. We need to remember this when interpreting the standard classifications. You'll often see, for example, a CT marked Class C 400V. The 400V refers to the allowable volt drop across the burden to keep within the 10% tolerance. So if we wish to pass 100 amps through the relays, that is 20 times rated current of 5 amps, through the secondary CT, we must limit the burden to 4 ohms. 100 amps times 4 ohms equals 400 volts. In this arrangement, the CT will be 90% accurate at least. For the same CT, if the burden is 8 ohms, the CT would only retain 90% accuracy for up to 50 amps, that is 10 times rated. Now let's turn our attention to voltage transformers, VTs. In many areas, these are called potential transformers, PTs. Either term is recognized and understood. In contrast to the CT, the voltage transformer has primary and secondary windings of many turns, both with high resistance to current flow. As a result of this high impedance, the current flow is very low, and the voltage in the secondary suffers little or no distortion in representing the primary. The secondary voltage is usually 120 volts. Many protection relays require line-to-line voltage as an input. For this case, 2 VTs are used, connected like this. This actually provides an open delta arrangement on the secondary, and thus we have all 3 line-to-line voltages. Where line-to-neutral voltage is required, such as in generator protection, 3 VTs are normally used, connected like this. At higher voltage, say 115 kilovolts and up, instead of connecting the primary across the power system, a coupling capacitor is often used. This is commonly called a CCVT. The string of capacitors is connected line to ground, and the VT primary is connected across one section. That is at lower voltage, but still representative of primary voltage.
Now, the VT does not suffer the same problem of saturation as the CT. This is because faults usually cause a voltage reduction, not an increase. In the case of a system disturbance, the system voltage may rise, but certainly not sufficient to bring the VT to saturation.
How is the VT affected by burden? Well, this is different than the CT. Additional potential coils are connected in parallel, not in series, so the circuit impedance falls. Hence, more current flows in both the primary and the secondary. The effect of the increasing burden could eventually increase the PT's output current above its operating level and so introduce inaccuracies. With most voltage transformers, the burdens are expressed not in ohms, but in terms of what the transformer must be able to supply in volt amps. Experience has shown that generally the VT does provide good reproduction of primary voltage, both transient and steady state, with sufficient accuracy for protection functions.
At this point, let's take a well-earned break, and then we'll come back and look at a subject which is vital to VTs and CTs, polarity. For now, switch the tape off and go through this material in your workbook. In connecting up instrument transformers to relays, it's obvious that we have to pay particular attention to the direction of current flow, that is, polarity. In discussing polarity in an AC circuit, we are referring to instantaneous values of voltage and current.
But what is meant by polarity? As an example, look at this typical transformer. Here, the primary and secondary windings are wound on separate legs of the core. They can be wound in either the same or opposing directions. Note that here, both primary and secondary windings are in the same direction. If the windings are wound in the same direction, the secondary current flows in the same direction as the primary. The polarity of the transformer is termed additive. We can see that current flows out of the secondary winding at the opposite end to current entering the primary. To help identify this, the terminals are marked like this. By convention, H refers to the primary and X the secondary. H1 is current into the primary and X1 is current out of the secondary. Conversely, when primary and secondary turns are wound in the opposite direction, the secondary current flows in the opposite direction to the primary current. The transformer is said to have subtractive polarity. Here, the secondary current flows out at the same end as the primary is entering, and the terminals are marked accordingly. In instrument transformers, the windings are almost always opposing, that is, subtractive. On schematic diagrams, the CT is often shown like this. The plus sign indicates where the primary current flows in and where the secondary current flows out. You will also see CT polarity markings shown as X's, dots, or even squares. This identification enables us to connect the secondary windings to the relays in the correct relationship. The same polarity rules apply for potential coils. The voltage transformer is marked on both the primary and the secondary.
Before connecting a relay to a CT, it is advisable to check that the polarity markings are correct. One of the most common methods used to determine polarity is the kickback method.
In this method, a DC moving coil voltmeter is connected across the CT primary winding, that is, the high voltage side, with the positive lead connected to the terminal marked H1 and the negative lead connected to H2. The positive terminal of a dry cell battery, typically a 1.5 or 9 volt, is then connected to the secondary terminal marked X1. The negative terminal of the battery is connected to X2 with an open switch in the line. Beware, the current applied in this test must be limited to a very low value. That is why a high resistance dry cell is recommended to prevent the core from becoming magnetized. Now, close the switch. When it makes, you should see an upscale kick of the meter if the polarity markings are correct. Take care not to apply the voltage to the high voltage terminals, primary in the case of a CT. Otherwise, an extremely high voltage will be induced into the secondary.
Voltage transformers can be checked in the same manner, but another check can also be used by applying 120 volts AC on the primary.
As this is a 10-to-1 step-down transformer, we should read 12 volts across the secondary terminals. Jumper a primary and a secondary terminal on one side of the transformer. Connect a voltmeter between the two terminals on the other side of the transformer. Because of the jumper, the voltmeter will feel the effects of both the source voltage and the induced voltage. In this VT, the windings are connected in a subtractive configuration, so the induced voltage is in phase with the source voltage. The voltmeter responds to the difference of the two in-phase voltages. Therefore, on our meter, if the terminal polarity is correct, we should read 120 minus 12 equals 108 volts. For an additive transformer, the induced voltage is out of phase with the source voltage, and therefore we should read 120 plus 12 equals 132 volts. You can see now where the terms additive and subtractive come from in referring to polarity. Of course, there are other ways of checking polarity, and some equipment that's available also checks ratios. Polarity is extremely important when it comes to connecting up three-phase transformers. Let's consider the case of a distribution transformer, say 4,160 volt primary to 416 volt secondary connected Y-Y. This could be a three-phase unit or three separate single-phase transformers as shown here. On a single line diagram, this arrangement would probably be shown like this, with the Y-Y symbols indicating the connections. More detail will be shown on the circuit diagram. First, let's look at the primary. The polarities are clearly marked. Here, the positive terminal of each primary is connected to its respective 4,160 volt line, while the negative terminals are connected together to form a common neutral. The line to neutral voltage is 2,400 volts. This forms the Y connection, and the phase relationship for each primary will appear 120 degrees apart, like this. Now remember, there are three separate transformers, each of 10-to-1 ratio. The voltage induced in each secondary, 240 volts, will be in phase with its respective primary. In certain cases, they may be 180 degrees out of phase, but for simplicity, we will consider the secondary voltages in phase. Now look, we have three secondary voltages available, displaced at 120-degree phase angles. They could be connected to form a delta arrangement like this, or a Y connection like this. By following the polarity markings, we now have the correct phase relationships and line-to-line voltage, 416 volts. But suppose we had inadvertently connected, say, phase A the wrong way around. Now the A line would be seeing a negative voltage, and the phase relationship would look like this. Phase A is now 180 degrees out of phase. And look at the line voltages. Instead of 416 volts, we now have only 240 volts between lines A and B, and the same thing between A and C. Many relays operate by comparing phase relationship between voltage and current, or perhaps some other quantity. A typical example is the directional sensing relay that we discussed in the previous videotape. Here we see typical connections for a directional ground fault relay. This 33 kilovolt bus is being fed from the secondary of the transformer, which is Y connected and has a grounded neutral. The outgoing feeder is protected by this breaker, and the three line CTs are connected to the sensing coil of the directional relay. Note the polarity of the CTs is clearly marked on the schematic. In this particular scheme, the polarizing quantity is obtained from the main transformer neutral, so this is current polarization, not voltage. Again, the correct polarity for the neutral CT is marked on the schematic. The correct polarity is also marked on the relay. So let's see how this works. A ground fault on the line would cause a return current to flow up the neutral, and consequently current will flow through the relay polarizing coil in this direction. At the same time, the line CTs will sense the out of balance due to the ground fault, and current will flow through the relay sensing coil in the correct direction to allow the relay to trip. For a ground fault on the bus, the current flow would be in the reverse direction and so block tripping. You can see how important it is to get polarity right when making connections. If either of these relay connections is reversed, the relay would perform completely opposite to our needs. It would allow tripping for ground faults outside the zone and would block tripping for those within the feeder.
Okay, so at this point, let's take a break, and then we'll come back and talk about phasor diagrams. For now, switch off the tape and thoroughly go through this material in your workbook. In the last segment, during our discussion on polarity, we looked at the voltage relationships between three interconnected single-phase transformers. You'll remember this circuit diagram, but in order to understand this, it was necessary to also study the diagrammatic representation of the phase relationships between the various voltages on both primary and secondary side. This diagram is known as a phasor diagram. It shows the magnitude and the phase relationship between the various voltages in the system. This is for a fixed moment, an instant in time. This situation is similar to the merry-go-round. When you stand on the sidelines, you see the red, white, and blue horses passing before your eyes. But if you stand on the merry-go-round, all the horses appear to be stationary. Now, let's go back to our phasors. We know that in practice, all of these values are constantly changing their position, rotating at the same speed as our system frequency. But it is important to note that the relationship between all of the values remains the same. And after all, this is what we are really interested in. So for the purpose of study, it's convenient to hold the rotation and fix all of the values, just as though we are rotating with the phasors. For example, let's look at this simple representation of a single-phase voltage and its associated current. The length of this line is proportional to the voltage, and similarly, current is represented by this line here. Normally, the magnitude represents RMS value of voltage and current, the values indicated by most meters. Phasors were referred to as vectors in the past. But some years ago, the term phasor was adopted so as to distinguish this diagram from a vector diagram as used in space and surface navigation. I'm sure you'll continue to hear the term vector used, but phasor is the correct terminology. This angle between voltage and current represents the phase angle displacement. In this case, the current is lagging the voltage. We know this because this arrow shows us that the phasors are rotating in a counterclockwise direction. And from our position in space, we will see the voltage phasor before the current. You may occasionally see the arrow indicating clockwise rotation, but normally the arrow is not shown because the generally accepted standard is that phasors always rotate counterclockwise. Here, we're looking at voltage and current in one phase only. When we add the other two phases, the phasor diagram will look like this. We can see that it is a perfectly balanced system. There is 120 degrees displacement between the voltages of phases A, B, and C. Also, the magnitudes of voltages and currents are the same, and the phase angle between voltage and current is the same in each phase, so we have a balanced load. Bearing in mind the counterclockwise rotation, the phase sequence, or phase rotation as it's sometimes called, is A, B, C. From our position in space, we would see passing in front of our eyes phase A, then B, then C, and then A, and so on. However, some power systems work on a different sequence, ACB, and in this case, the phasor diagram would be relabeled like this.
This delta Y transformer is feeding a three-phase, four-wire distribution line. A delta Y transformer has a 30-degree shift in voltages and currents between primary and secondary. In fact, as this example will show, the polarity markings and connections shown here have the primary leading the secondary. The neutral is grounded. First, phase relationships on the Y-connected low-voltage side. Plot the phasors for each phase voltage, that is, from line to neutral. Starting with line A, we plot VAN on the vertical reference. Note we could have used a horizontal reference. As this is a Y-connected secondary, we can now draw the other line-to-neutral voltages, VBN and VCN, each at 120-degree phase displacement. The phase sequence in this case is ABC. Also note, we are using lowercase letters to denote secondary phasors. But what about the line-to-line voltages? For example, line A to B. To get VAB, we go from line A to neutral, VAN, and from neutral to line B, VNB. VNB is the reverse of VBN. So now we must add VAN and VNB to get phasor VAB. We find that VAB is leading VAN by 30 degrees. Similarly, the voltage between lines B and C, that is VBC, is leading VBN by 30 degrees. And the same relationship goes for VCA. Let's now take a look at the relationship for current. Considering the load to be at unity power factor, we know that the line current IA is in phase with the line to neutral voltage VAN. So we can draw the IA phasor along phasor VAN. Similarly, IB is in phase with VBN, and IC is in phase with VCN. Of course, if the power factor is, say, 0.95 lagging, then all of the currents will be offset by 18 degrees. So much for the secondary. But let's move over now and draw the phasor diagram for the primary of this transformer. Usually, the primary and secondary phasors are drawn on the same diagram, but in this case, for clarity, we'll construct a separate phasor diagram. Note that the primary is connected in delta. Phase A is connected between line A and C, phase B between line B and A, and phase C between line C and B. Now remember, for each phase winding of this transformer, the voltage on the primary and secondary sides must be in phase as they are wound together on the same leg of the core. So when we draw the first voltage phasor for phase A, the voltage vector, that is VAC, must be along the same line as VAN in the secondary side phasor diagram. We're using capitals here to define the primary side of the transformer. The primary voltage on phase B, that is VBA, will accordingly lie along the same line as VBN, and similarly with VCB. Sometimes confusion can arise because the phasor diagram looks like a Y arrangement, but we know that this primary is connected in delta. An important point to remember is this phasor diagram is not meant to show electrical connections, only phase and magnitude relationships. We know that delta connection phasors can be shown like this. But if you look at the direction of voltage here, A to C, here B to A, and here C to B, you can observe that they are the same. So Either phasor diagram can be used to represent delta or Y circuit connections. Now let's look at the currents in the primary with a unity power factor load. Clearly in phase A, IAC primary is in phase with IA secondary. Similarly, IBA primary is in phase with IB secondary. And likewise, ICB is in phase with IC. Therefore, IAC is drawn on the phasor diagram in phase with IA, and IBA is drawn in phase with IB. Similarly, ICB is drawn in phase with IC. But what is the current in line A, that is IA? Well, look, clearly the line current IA is the sum of the phase currents IAC and IAB, which is the reverse of IBA. Therefore, plot IAB on the phasor diagram and add IAC, which gives IA. We find by inspection that the line current IA will be 30 degrees ahead of its respective phase voltage VAC. Similarly with line currents IB and IC. IB equals IBA minus ICB, and IC equals ICB minus IAC. So there is a 30-degree phase shift of currents as well as voltage in a delta Y transformer, as you would expect. The line current IA in the Y-connected secondary is 30 degrees lagging the line current IA in the delta-connected primary side. Comparing the phasor diagrams, we can study the relationship between primary and secondary voltages. First, for clarity, remove all primary currents. Then superimpose the secondary line-to-line voltages on the primary voltages. Then reverse CA to AC, AB to BA, and so on. Look, now VAC secondary is lagging VAC primary by 30 degrees. And the same thing goes for the other line-to-line voltages. This is an important conclusion. This delta Y connection produces a phase shift of 30 degrees. Moving from high voltage delta to low voltage Y provides a 30-degree lag, and vice versa. This is, in fact, in accordance with the ANSI-IEEE standard, which states that for Y delta or delta Y transformers, the high voltage side should lead the corresponding low voltage side by 30 degrees. Now, if the transformer is Y delta, then different connections must be made to achieve the 30-degree lag on the low voltage side. Here we see the arrangement and the corresponding voltage phasors. You can see that the secondary phase voltage VAB is wound on the same leg as the primary VAN. So they can be drawn on the same phasor. But look, the primary line-to-line voltage VAB is 30 degrees in advance of secondary line-to-line VAB. Similarly with VBC and VCA. So the ANSI rule has been observed. The high side voltages lead the low side by 30 degrees.
Now, I am sure you can see, even from this relatively simple example, just how useful the phasor diagram is. To simplify matters, we have generally been looking at the unity power factor situation, but clearly the diagram can be used to show the effect of different power factors. Also, the effect of unbalanced load, both the magnitude and phase displacement. The phasor diagram is indeed a very valuable tool, and we'll frequently make use of this in our future studies. I'm sure you'll be pleased to know that we have included several examples for you to work through in your workbook. For now, let's take a break. Please switch off the videotape and thoroughly review this material in your workbook. In this section, we'll look at the convenience of using the per unit system. Please note, however, we're not dealing with the complex subject of fault analysis. For example, in this simple system, the 220 MVA generator supplies the load at bus B by feeding power through the two transformers and the connecting transmission lines. Note that we have several different voltage levels: 23 kV at the generator terminals, 230 kV along this transmission line, and 115 kV to the load. Now suppose there is a direct three-phase fault on line B close to the load. The voltage between phases at the fault will fall to zero, as there is a dead short circuit between them. But the generator will continue to feed the fault, and the only resistance to current flow is the total impedance of this circuit. That is the sum of the impedance of each transformer, of the line conductors, and also the generator winding itself. You will remember we discussed this in the first tape in the series. But how do we know, or how can we find out, the value of impedance for each item of equipment? Well, quite simply, it's usually marked on the schematic and also on the nameplate of the equipment itself. A typical example is this transformer. The nameplate shows that it's rated at 46 MVA, 230 kV primary, 115 kV secondary. The impedance is indicated as 10%. But shouldn't the impedance be indicated in ohms? Well, the answer is yes and no. Not necessarily, and I'll show you what I mean. If we do need to calculate ohmic impedance, we must remember the relationships between VA, voltage, current, and impedance. First, VA, voltage times current, and that equals voltage times voltage over impedance Z, or V squared over Z. By transposing, we find that Z, impedance, equals V squared divided by voltamps. In terms of the power system, impedance per phase equals kV squared divided by MVA. In this expression, the kV and MVA units are quite compatible because we are squaring the kV and so bringing another 3 zeros into the top line. And by using line-to-line voltage, we get impedance per phase. The MVA value is total three-phase. Verify these units using your workbook. Using this expression, we can calculate the impedance of the load, including line impedance being fed by the 46 MVA transformer. The ohmic impedance of the circuit under rated load equals 115 kV squared divided by 46 MVA equals 287.5 ohms. The nameplate informs us that the short circuit internal impedance of the transformer is 10% of the rated circuit impedance. So if a three-phase fault occurs at the transformer terminals, the impedance will fall to 10% of that 287.5, that is 28.75 ohms. This is the internal impedance per phase of the transformer. But wait a minute, we may just as well have inserted the 230 kilovolt value for the transformer voltage instead of 115 kV. In this case, the ohmic impedance would come out to 230 kV squared divided by 46 MVA times 10% equals 115 ohms. This is an important conclusion. The ohmic impedance of the transformer is much lower when measured or seen from the low voltage side. This means that in order to add the different impedances in the system or perform calculations, we'll have to do a lot of number crunching as we go from one voltage level to another. Far better, then, to establish a base value and use the percent or per unit system for expressing the quantities VA, voltage, current, and impedance.
Of course, percent or per unit are the same thing. 10% is the same as 0.1. Either system is used, so be alert for drawings showing impedance as, say, Z equals 5% or Z equals 0.05. Incidentally, the drawings will more often indicate the per unit values for X, that is, reactance, instead of Z impedance. This is because, from the point of view of fault calculations, most of the impedance is made up of reactance. Also, it is more correct to arithmetically add reactances than impedances, which may be at different phase angles. Either way, the difference is not significant. Hence, the use of X values is quite acceptable and satisfactory.
So now that we've established the utility of the per unit system, let's look a little closer. Usually, base voltage and base voltamperes are chosen arbitrarily, and then base impedance and base current are derived from these.
Base voltage should be chosen to be the nominal voltage in particular parts of a system. In our example, that would be 23 kV, 230 kV, and 115 kV, base voltage for these specific areas. Clearly, we will have several different voltage bases on most power systems. For example, an actual voltage of 255 kV divided by 230 kV base voltage gives us 1.1 per unit. On the other hand, a voltage of 110 kV on a 115 kV base gives a per unit value of 0.96 per unit. So you can see another advantage to using per unit quantities. Under normal operating conditions, all system voltages are close to 1 per unit, so errors in the calculations and system abnormalities are easier to spot. It is important to remember that the base voltage always indicates three-phase line-to-line volts, not line-to-neutral.
The value for base voltamperes is chosen arbitrarily, and it must be used consistently throughout all of the calculations. Unlike the voltage base, there is only one base voltamperes to be used throughout the whole system. This is very often chosen to be 100 MVA. 100 MVA is a nominal magnitude for most power systems, and a number easy to work with. This base is used for both megawatts and megavars.
For example, 250 MW would be 250 MW actual power divided by 100 MVA base power, or 2.5 per unit. Similarly, 90 MVAR would be 90 MVAR's actual reactive flow divided by, again, 100 MVA base power, or 0.9 per unit. If the value for base impedance is required for any area of the system, it can be derived from the voltage and power bases. This is the expression: base impedance equals base kV voltage squared divided by the MVA base. However, we can very easily calculate the per unit values directly. Let's take our 115 kV transmission line, which has an inductive reactance of 0.53 ohms per mile. We know the line is 20 miles long, giving a total reactance of 10.6 ohms. As we have already mentioned, quite often only the reactance is taken into consideration, as line resistance is very low. Now let's convert to the per unit system. We already learned that ohmic impedance is given by the expression impedance per phase equals kV squared divided by MVA times per unit impedance. Transposing this, we find that per unit impedance is equal to MVA divided by kV squared and multiplied by the ohmic impedance. Using a power base of 100 MVA, the per unit impedance for the 115 kV line equals 100 MVA divided by 115 kV squared times 10.6 ohms equals 0.08 per unit, or 8%.
It is extremely important whenever quoting per unit impedance values, you must always include the associated value for base MVA.
In actual practice, the ohmic value is not really of great interest. For example, we are considering a three-phase fault right at the end of the 20-mile 115 kV line. In calculating available fault current, our first job is to add up all of the impedances along the route to the fault. First thing we see when looking at the per unit values on the drawing is that they refer to reactance X. These values usually are based on the equipment rated capacity unless otherwise noted on the drawing. So we have to remember to convert equipment per unit reactance to the selected 100 MVA base. Let's do this. The generator transient reactance is given as 0.16 per unit. The term transient refers to the changing conditions which occur initially during a fault. The generator is rated at 220 MVA, so in order to bring the reactance to our common 100 MVA base, we must multiply by 100 and divide by 220. The corrected value is 0.073 per unit. Mark this on the diagram. Similarly, the step-up transformer reactance, 6%, must be reduced from 250 MVA to 100 MVA base. This gives us 0.024 per unit reactance. The 230 kV transmission line indicates per unit reactance of 0.25 on a 250 MVA base. This converts to 0.1 on the 100 MVA base. We already know the impedance, let's call it reactance value for this transformer, 10% at 46 MVA. That is 0.217 per unit on a base of 100 MVA. The 115 kV line we already calculated as 0.08 on a 100 MVA base. So, what do we do now with all of these 100 MVA base values of reactance? Well, as the fault is at the end of the line, summating gives us a total per unit reactance to the fault of 0.494. And remember, this is calculated on a base of 100 MVA. This means that when a fault occurs on the end of the line, the circuit impedance will fall to 0.494 of its value at 100 MVA load. As impedance falls, the MVA delivered to the fault will rise, and its value can be found from this simple relationship. Load MVA divided by fault MVA equals load Z divided by fault Z equals per unit impedance. And from this, fault MVA equals load or base MVA divided by per unit impedance. Accordingly, we can say that on our simple system, the available capacity at the fault will be equal to 100 MVA divided by 0.494, the per unit value. This comes to 202.4 MVA. Of course, if required, we can now get fault current knowing fault MVA and line voltage. Now, another fault condition. What would be the fault level if a three-phase fault occurred on the generator terminals? This would be 100 MVA divided by 0.073, the per unit impedance. This comes to 1,370 MVA. We get the same answer directly from the nameplate. That is 220 MVA, the generator rating, divided by the per unit impedance, 0.16. Observe that the generator is greatly overloaded in the immediate few cycles after the fault, before the protection system operates.
I must emphasize at this point that we are not trying to show you how to carry out fault calculations, but rather the advantages of the per unit system. As you well know, fault calculations are far more complex. We will, in fact, be looking more closely at fault characteristics in the next tape. At this time, please switch off the tape and review this material in your workbook.